So for this part, Shabab, the objectives is to discuss the steady-state performance of universal motor, discuss the application of universal motors, understanding the DC and AC excitation of universal motors, and discuss the power electronic converters used to control universal motor. طيب, as we discussed, Shabab, in the first class, this was a chart of electrical machines or electromechanical machines, and we could say that we have DC machines, we have AC machines, and special machines. As you can see, for DC machines here, there is permanent magnet DC machine, shunt, separately excited, series, compound. We covered most of these, Shabab, in our course. طبعا shunt and separately excited, we solved lots of problems. Series, we may have few problems in series. Compound, it's include both of series and winding. There are two types of compound, long shunt and short shunt compound motors. We did not solve some problems regarding that, but the theory is similar to other motors. Okay, only permanent magnet DC motor is not covered in our course. However, it's very simple and similar to other motors. For AC machines, we cover the induction machine, we cover synchronous machine, we cover three-phase, wound or squirrel cage, we cover synchronous machine, salient and cylindrical type, but we still have capacitor start, single phase, split phase, and the capacitor run motors. These are single phase induction motor. So for single phase induction motor, we didn't cover it yet. We will cover, inshallah, during next few classes. Then we have something called the Shabab special motors. Special motors, comparing with the DC machines and the AC machines, it's special, which means the supply is not all of time DC or AC. It's special, different a bit. Like what? Like stepper motor, we will cover it, inshallah, during our classes. Brushless DC motors, you already familiar with this type because we discussed it as a part of synchronous machines. So brushless DC motor is a part of synchronous machine. However, because it has some special design, sometimes it can be categorized as special motors. Also, there is type of motors called hysteresis motors. Some others called reluctance motors. Okay, but these will not be covered in our classes. We will cover universal motor because it's used a lot in our home appliances. Okay, and stepper motor because it's used a lot now in renewable energy. So these are the machines we already covered and what we still need to be covered, inshallah. So today, inshallah, we will focus on universal motor. What's the universal motor exactly? Here, this is a small demonstration video. We can listen together, Shabab, to the video, but I believe I need first to reshare with computer sound. So I will start, Shabab, the demonstration video. If you cannot listen to the video, please let me know.
Universal motors. They are capable of running under both DC and AC power supply. This unique feature makes them preferable for many special types of applications. A universal motor is a specially constructed DC series motor. Let's consider a simplified series motor. When connected to a DC power source, they work just like a DC motor. With the help of commutator rings, a unidirectional current is always made to flow through the left and right side of the coil. Thus, the torque action is always unidirectional and the rotor continues to rotate. Let's see what happens when the same motor is connected to an AC power source. Since the field coil and rotor coils are connected in series, the same phase of electricity passes through them always. It is obvious that, in this case, the electricity flow through the left and right part of the coil is never unidirectional. But along with the change in direction of this current, direction of magnetic flux also changes, as the same electricity flow through field and rotor coils. This simple trick will make sure that the torque action is always unidirectional. Here are the different scenarios that could occur during the motor rotation. It is clear that irrespective of speed of the rotor and frequency of electricity, the torque action is always in the same direction.
Is it clear يا شباب؟ يعني for the same motor, if we change the supply from DC to AC, both of current and the flux will be a bidirectional current and a bidirectional flux, and this will keep the torque moving in the same direction like in DC. So this is now the difference if we supplied this type of motor by DC supply or AC supply. You will have the same direction of torque, which means the motor can rotate in the same direction, whatever the supply, if it is DC supply or AC supply. Is it clear يا شباب? Is this part clear here in this video?
Yes.
Any question يا شباب regarding the operation? يعني it's similar to DC motor. Similar to DC motor, and as you could see here, the flux direction in DC will be constant according to the applied polarity of the commutator here. Okay, طبعا it will be reversed if the commutator converted from positive to negative. The supply current and flux will be reversed together, and because it's reversed together, this will keep the torque in the same direction. This is going to up in the left hand side, and in the right hand side the force is down. So according to these two forces and the distance between them, there will be a torque in that direction. Okay, so this is now considered the rotation direction of this motor. So if you reverse the polarity of the commutator, okay, due to the positive and negative half rings, this will keep the torque moving in the same direction. And it will be the same also for AC supply, because whatever the polarity, AC or DC now, the torque will have the same direction. So, and this is the importance here in this video. Now, let's define some properties for this type of motors, شباب. Single phase series motors. So we can consider it, by the way, as a type of induction motors. However, instead of induction motors of squirrel cage type, okay, we have here two windings. It's one type of the single phase induction motor called split phase. So we have in split phase induction motor, if we connected the split phase together in series, this will act as universal motor. Sometimes, شباب, this motor is called AC commutator motor. You know, commutators only exist in DC machines. However, if series DC motor is redesigned by such a way, and we will discuss why we should redesign, okay? If it is redesigned in terms of the mechanical cores in such a way, we can supply it by AC. And in this case, it will be called universal. So it's universal, شباب, because we can supply it either by DC supply or AC supply. For that, we call it universal. The given name universal is because we can supply it by DC or AC. They are widely used in fractional horsepower ratings. So this can be used, شباب, for small power machines in many domestic appliances, such as portable tools, drills, mixers, vacuum cleaners, but small vacuum cleaners, because يعني large vacuum cleaners are made of induction motors, okay? And these motors are usually light in weight and small in size, by the way. It's very small motors, okay? And speeds can vary between 1500 RPM to 10,000 RPM, okay? So it has the advantage of high speeds. Also, universal motors are mostly operated from single-phase AC source. As we said, it could be supplied by DC. However, you know, the available supply at homes are AC supplies. It's not DC. At homes we have AC supply, so it's usually used or supplied by single-phase AC source. Therefore, both the stator and rotor structures are made of laminated steel. So this is now the difference between series DC motor and universal one. If you design a DC series motor, you should make the core laminated in order to reduce the core losses because of eddy current losses. You know, core losses, we discussed the core losses before. Did we discuss core losses in details? Did we discuss the core losses in details?
No.
Core losses for any AC machines. Let me add one more slide here to just discuss more about the core losses. Core losses are divided to many parts. One is called eddy current loss. One is called hysteresis loss. And a third terminal, this is called excess loss. Eddy current loss, you know, for any magnetic core, the core is iron, is made of iron. So, because the flux is like AC, and this flux is cutting already a material, so it's expected to generate EMF within this material and start flowing a current. This current is considered as eddy current. We call it as eddy current. So this eddy current will make losses in this core itself, like any current making copper loss in any resistance. So this is called eddy current loss. So this eddy current loss is a function of frequency to power x. Okay, power x may be fraction, by the way. Fine. Also, there is something called hysteresis loss. I think all of you are familiar with the hysteresis band. You know, this is the BH curve for any material. So for any motor, you will find something called BH loop, like that. This BH loop, it's a relation between flux density and flux intensity. This BH loop has internal area. The summation of this area, is considered as the hysteresis loss. So this is considered as the hysteresis loss. So hysteresis loss is the surface integration for BH curve. Okay, so this is now considered as the second type of core losses. Yani until few decades, only the core losses were classified to these types, eddy current and hysteresis. However, after applying variable speed drives to electrical motors, yani we could find that there is another part of losses, yani could be measured from devices, and if we make the calculations of eddy current and hysteresis, yani it's not appearing like that. Yani we calculate the values. Let me give you an example. If we operate a motor using sinusoidal supply, you may, for instance, find 100 watts eddy current and, for instance, 200 watts hysteresis loss. So we can say B core equals 300 watts. However, if we make the same by supplying the motor, not by sinusoidal supply, this time, but supplying by variable speed drive. You will find the total power is not 300. It's more than 300. And you already know that the equations of eddy current and hysteresis equation, by the way, it's empirical equation made by means of curve fitting equations like that. Okay, so it's not derived equation based on mathematical models. It's just curve fitting equations. But as I said, by making experimental measurement for the core losses due to voltage source inverters or variable speed drive, we could find that the power is higher than this amount. The scientists did not give a certain name for this power, but they said it's excess loss, which means it's added losses to these types. They did not give any scientific name for this power, because we cannot give it a name because it's not driven, but it's just observed by experiments. So we call it now as excess loss. So these excess losses are due to the harmonics, because of the harmonics coming from the power electronic converters. It could be observed in terms of BH loop. For this BH loop, I will take a part of the BH loop like that. For instance, instead of making BH loop, this part in sinusoidal wave will be like that. This part, if we zooming in, it will be like that. However, this is due to sinusoidal supply. However, if we make it due to power electronic converters or variable speed drive, this line will appear like that. Instead of having a straight line, it has many internal loops. For that, the area of the BH loop will be different now. So this is the reason of the excess power, because of the extra inner loops of the pH curve itself. And this is coming because of voltage source inverters. Okay, so this is now, shabab, the different parts of core losses. So now for AC supply, you have core losses. It's not like DC motor now. So you have eddy current loss. For that, shabab, we prefer to make the core in laminations. Why in lamination? Because lamination will reduce the eddy current loss. So this will minimize the eddy current loss and hence reducing the overall core losses and lead to higher efficiency. So the difference between DC series motor and universal motors, even if the universal is supplied by DC supply, the difference is the core lamination is different. This is why. This is because of the reduction or design to reduce the eddy current loss of the machine. Also, comparing the brush resistance, it will be different a bit in universal motor because it needs to limit the AC current also. Right. High power AC excited universal motors are used in trucks application, but this is rarely found in Japan. For high power used in trucks, you can rarely find now universal motors using in trucks. The recent technologies of electric vehicles are preferring, for instance, permanent magnet types or switched reluctance motor, not universal type motors. Okay, shabab? So, maybe in very small trucks, it can be used. However, in vehicles and powertrains, they prefer the use of switched reluctance and permanent magnet synchronous motors. Now, in terms of mathematical modeling, let's see together what is the mathematical model if we supply the machine by DC source. If we supply the machine, shabab, by DC source, so the excitation DC source can, for a separately excited DC motor, can be described as not separately excited, it's for series DC motor, sorry. So this is here, need to be changed. This is for series DC motor, shabab. Series excited motor can be described as, we discussed these type of relation, shabab, before. For series DC motor, EA, the EMF equals K series multiplied by armature current by speed, and you know torque equals K series multiplied by IA. And you already know the relation also of omega, which is the motor speed, which is E over K series IA. And if we have rheostat in series with the armature and series windings, so the relation will be omega equals Vt minus IA multiplied by the total resistance divided by K series IA. So this is now, Shabab, the relation of omega. And you know also the characteristics of separately excited, of series excited DC motor. If you increase the value of rheostat, so the characteristic will move in that way. So this is, Shabab, yani what we already discussed previously regarding series DC motor. There is no difference, Shabab. The same like previous DC motors. Now, if we supply the machine by AC, what will be the difference? Firstly, if eddy current effects are neglected, assume we are going to neglect the eddy current loss because we already made the core in laminations. So we can say now IA and flux phi D are in phase. So this type of Shabab is designed to have IA and phi D, which is the direct component of flux. You know, for any AC machine, Shabab, we can analyze the motor in different ways. Something called ABC modeling, and some are called DQ0 model. Yani these models are preferred because it's simpler in solution. If we made the machine in the different reference frames, we hinted before about the reference frame theory. We said that we have stationary reference frame, we have rotor reference frame, and so on. So for all of types of machines, Shabab, we prefer to use DQ model instead of ABC because the parameters will be simpler in solution and modeling will be much easier. So you will find for this type of motors, phi D is in the same direction of IA. This means that the armature current and the induced EMF will be in phase. So if we make a relation for IA, we can say IA equals IA maximum cosine omega t. طبعا cosine or sine يا شباب similar, okay? And phi D will be in phase, so it's also phi D maximum cosine omega t. Now, the instantaneous EMF value can be calculated as EA equals Ka phi multiplied by omega. But all here are considered as variable, not DC values. So we have Ka, this is a motor constant, phi D maximum cosine omega t, which is the flux, and multiplied by motor speed. So if you would like to calculate the RMS value, because now it's considered as AC motor, so we need to calculate RMS values. We can take the RMS as maximum over square root of 2 in order to get the RMS value. So we can say now Ka phi D maximum over square root of 2 multiplied by omega m. So we can say finally Ka phi D, and this is considered as RMS value. This is RMS value multiplied by omega m. And you know, because this is series motor and this flux depends on the field current, which is the same as armature current here, we can make the same like what we made already in DC series motor. So we can say now Ka phi D equals another constant K series multiplied by IA, which is the armature current, which is the producing already the phi D, and also multiplied by motor speed. So this is now the relation of RMS of the EMF. Now, regarding the mechanical equation, the torque equation, you know, for motor, for this kind of series motor, we can say that T, torque of T as a function of time instantaneously, equals Ka phi D multiplied by Ia. You know, Ia is a vector and phi D is a vector also. So now the relation is Ka phi D maximum, Ia maximum, cosine square omega t, because each of them is cosine omega t. If you get the equivalent equation of cosine square angles, it will be like that, Shabab. Ka multiplied by phi D maximum, Ia maximum over 2 multiplied by 1 plus cosine 2 omega t. 2 omega t, it means the frequency is doubled now. So it's double of the supply frequency. So as you can see here, you have maximum over square root of 2 multiplied by maximum over another square root of 2, because 2 is nothing by square root of 2 multiplied by square root of 2. So we can say now Ka multiplied by phi d RMS multiplied by Ia RMS multiplied by 1 plus cosine 2 omega t. This is the instantaneous torque value. However, the average torque value, when you calculate the average, you know the average for cosine 2 omega t is 0. So finally, you can say the torque equation as the average value equals Ka multiplied by phi d multiplied by Ia. And what we made here is similar. Ka multiplied by phi d equals K series by Ia. So we can finally say that torque equals K series Ia squared. Similar to the series motor equations. So there is no difference in equations between DC and AC. But in DC, we have all as constant values. However, in AC, we have average torque, we have RMS EMF. This is the only difference. This is the phasor diagram of our AC universal motor. So the power or the volume of the power can be calculated similarly like before. It's EA multiplied by IA. You have the relation of EA and IA, you can calculate it. And the developed torque equals B gap over omega M, which is EA IA over omega M. So this is now the relation of torque and power. In terms of phasor diagram, the same relation, VT equals IA multiplied by RT plus JXT, because now you have inductance. In DC, the inductance at steady state was 0. However, here, if you supply it by AC supply, you will have a value for inductance. This plus the value of EA, and this is now the representing phasor diagram for the universal motor. Right. I don't know if the time is sufficient now to continue. No, the time is due, so we can continue, Shabab, from this slide next class, inshallah. Any question, Shabab? Any question? Right. Okay. Thank you, Shabab, and we see you, inshallah, next class. Assalamu alaikum wa rahmatullah.
Assalamu alaikum.